Okay, so to quote Cannonball Run, we have a long way to go and a short time to get there. So we have 2 lectures left. We need to finish E2 and E1 and then get to addition reactions. In all likelihood, by Wednesday we won't finish that. So what I'll do is create a separate screencast, upload it into YouTube for you to watch so that you can use that for your exam 5 module, which opens Wednesday at 12:15, closes Thursday at 12:15. Your final exam is next week, Monday or Wednesday. I can't remember between my 2 classes which one it is, but it definitely starts at 10:45 a.m. It'll be in this classroom. It's the ACS final. If you look at your seat, there's a little number. The rows have letters. You'll get an assigned seat. I'll look at the SOAR photo roster to make sure that it's you sitting there. I'll post your seat assignments in Canvas before your final, so you'll sit in that seat assignment. The final exam, you have 110 minutes, so that's a little bit shorter than what the university gives you, just because it's a timed exam for the ACS. It's 70 multiple choice questions that will span all of the stuff we covered this semester. I would say Thursday afternoon or Friday morning, I'll upload your final total exam points for modules 1 through 5. That'll give you an idea of where your grade is. You can take those points, put them into the Excel file. It only calculates your grade based on the points so far, so it's not including the final, because the way the calculations work. If you have any questions about that, you can just email me. But by Friday afternoon, you should have a good idea of where your grade is headed as you go into the final. Any questions? Okay, so we were talking about the elimination reaction. And so remember, there were 4 atoms involved. The alpha carbon, which contains the leaving group, which I'm showing as X. Typically that's a halogen, such as chlorine, bromine, or iodine, or it's a sulfonate, and those are derived from alcohols. You have the beta carbon, which has the acidic hydrogen, and so that's abstracted by the base. The key thing to remember for elimination so in general, it's the formation of a pi bond. So right now, that pi bond, we're talking about alkenes. Organic 2 eliminations will focus on forming carbonyls. That's the CO double bond. So we'll talk a little bit about bases to begin with here. So oxygen bases are the most common because they are derived from alcohols. So you take an alcohol, you can deprotonate it, that makes an oxygen base. Remember, the action of a base is to abstract a proton. So bases abstract protons, but the complication here when we're talking about these mechanisms is that these reagents can also act as nucleophiles. So an acid-base reaction is strictly limited to proton transfer. A nucleophile is typically displacing something, so you're forming a heteroatom to carbon bond. As you start preparing to study for the final exam, that you're going to want to know the reactivity of these reagents. So common oxygen bases. So in our first column, we have the base name. So sodium hydroxide is in row 1 there. And then we have this new descriptor size, and we'll talk about why size matters for organic chemistry purposes only here. And then the conjugate acid of that base, and then the pKa. So with these eliminations, you can get away with using a pretty weak base, even though the pKa of that beta hydrogen is around 45 to 50. So when you substitute off the H from sodium hydroxide, then you make it a carbon group. These are all called alkoxides. So alkoxides, the negative charge is on oxygen, and as we go from methoxide to ethoxide to tert butoxide, notice the size of the base increases. The pKa's all relatively fall within the same range, 16 plus or minus 2. And as I stated before, you can typically make by taking the alcohol, so I'll designate the alcohol as R and then OH. And then you're going to add in the metal. So the little naught sign, the degree sign, that's just the elemental metal. You add it in small pieces. That's going to generate the alkoxide plus the metal cation, and then evolve hydrogen gas. So lithium, sodium, potassium, those are all metals you can buy. You cut them up into little pieces, throw it in there, they'll eventually dissolve. You see gas bubble out, that forms your base. So nitrogen bases, typically we're using tertiary amines. So that means the nitrogen is bonded to 3 carbon atoms. So the first one is a derivative of ammonia. So sodium amide is NaNH2. The size of that is small. Its conjugate acid is ammonia, and the pKa is 38. So you can see by the huge gap in those pKa values. Remember the inverse relationship between acidity and basicity. Ammonia is a weak acid, so therefore sodium amide is a strong base. So that's the one that's ionic. The rest of them are all polar covalent. So triethylamine, diisopropylamine, and then we use these abbreviations, not as complicated as that horrendous disease on the board there, but DBN and DBU. And so these are called amidine bases. So triethylamine, I've written large for all of them, but whether it's medium/large size is debatable. But what you notice is when that base deprotonates, it ends up with an ammonium, so the nitrogen is positive now. And then the pKa value that's shown is of that ammonium acid, so nitrogen plus. So those are bases that we can use in elimination. Why does the size matter? So the bulkiness of the base. So when we were looking at that 2-bromobutane, so there was our alpha carbon. We have beta and beta prime. Remember, we're only concerned about the hydrogens on the beta carbons. If we classified the number of them, that had 3 hydrogens, that had 2. So I hate to throw in a bunch of numbers here in the same color, but those were primary and those were secondary. When you move from primary to secondary to tertiary, the protons become less accessible. So you have all these substituents, they're crowding around that hydrogen. It's harder for the base to find that hydrogen. So as the bulk of the base increases, the more it will favor deprotonation of less sterically hindered hydrogens. And so within an elimination, depending on the size of the base, we can classify the outcome in two different ways. The first type of elimination is called the Zaitsev elimination. So that's going to use a small base, and it's expected to act upon the beta carbon with the least number of hydrogens. So the result of that is it's going to form an alkene that's more substituted. So this gets back to alkene stability. So for example, in the 2-bromobutane, if we were using a small base, we would expect it to go after the beta prime carbon that only has 2 hydrogens, because the elimination there is going to form the more substituted alkene. Alternatively, if the size of the base is large, say potassium tert butoxide, that is called a Hofmann elimination, and it goes after the beta hydrogens, the beta carbon that has the most hydrogens. So for 2-bromobutane, that would be the primary position, and then you end up with the least substituted alkene. So even though, based on the alkene stability, you want to form an alkene that's more substituted, you can alter that by choosing the size of the base. So Zaitsev, I would say the thing to remember, so Zaitsev gives you most substituted, and then Hofmann gives you the least substituted alkene. So I'm going to run through these questions pretty quick, just in lieu of the time that we have. So now we have 2-bromo, 2-methyl. So 2-bromo, 2-methyl butane, there's our alpha carbon with the leaving group. How many unique hydrogen sets are there? There's 3. So those are equivalent, those are primaries. We have a primary at the end of the chain, and then we have secondary. So we have 3 sets. In a ratio of 6 to 3 to 2. So remember now, since we're only dealing with beta hydrogens, the 6 and the 2 are the only ones that we have to consider. Those primaries that integrate to 3 at the end of the chain won't matter. So of the 3 sets, we'll call those beta and that beta prime. So you can see the logic here, we're funneling down from the total sets to just considering those on the beta carbons. And again, that ratio was 6 to 2. So the total number is 8. So if we classify them, that's just an easy analysis for us to do in terms of understanding how the base size is going to affect the product distribution. So statistically, 75% of those protons are primary, 25 are secondary. So again, we can alter where the base is going to abstract by looking at the bulkiness of that base. So if we were going to treat that with potassium tert butoxide, that's considered a large base. So the question says, which grouping of beta hydrogens is the most accessible to this base? So remember, we're only considering those betas. So these are classified as primary. Those are classified as secondary. We have a large base, so we want to go over the more accessible beta hydrogens. Those would end up being the primaries, and those are classified as methyls. And remember that a CH2 group is called methylene. So potassium tert butoxide is going to eliminate across the methyl group, so that's where we have to draw our double bond. So remember in E2, the 2 stands for bimolecular, so the concentration of the base and the substrate matters. So the base abstracts a proton. We do the elimination. We're forming the double bond between carbons 1 and 2. We still have a methyl group on carbon 2, and then the rest of the chain. This would also produce potassium bromide, and then tert butanol as the conjugate acid of the base. So what is the classification of the major product alkene produced from this? When we classify, remember we're looking at the sp2 hybridized carbons. We're counting the carbon substituents. So if we number this, we see that only carbon 2 has substituents. It has 2 of them, so that's di-substituted.
Does that say bis? Like, what's that meaning?
Oh, it says big, sorry. So big base, and then we can say small hydrogens, or easily accessible hydrogens. So remember that with a di-substituted alkene, there are a couple other further ways we could classify it. We have the 2 substituents residing on the same carbon. So this is called geminal substitution. if each carbon had a substituent, then you would look at the relationship of them, and they could be cis or trans. So in terms of naming this, it's a 4-carbon chain, so that's butane. It has an alkene, so that becomes butene. The start position of the alkene is at carbon 1, so it's a 1-butene. And then on the 2-carbon, we have a methyl group, so it's going to be 2-methyl-1-butene. So this question says, what is the name of the minor product? So the minor product is going to result from deprotonation of the other beta hydrogens. So again, that's less likely to happen because you have the large base, you have the accessibility limited to those hydrogens. So now we're going to eliminate across carbons 2 and 3. And then we end up with that as the minor product. So it's still 4 carbons long, but now the alkene starts at position 2. So it's a 2-butene. So that eliminates D and B. There's only one substituent on the chain that's at the 2 group, so this is 2-methyl-2-butene, so the answer is A. Any questions? So that was E2. So how do you diagnose that you have an E2 reaction? Typically, you're going to have a solvent, and then the conjugate base of that solvent, if it's an oxygen base, or you're going to have one of those tertiary amines. So now we're going to transition into E1. So this is elimination unimolecular. And what's complicated about this is the conditions resemble SN1 quite a bit. So you're no longer going to have a strong base present. So typically you'll have solvent and most likely an acid promoter. And again, that looks like SN1 conditions. So overall in a reaction, if you have your leaving group, say it's tertiary, so it falls within either SN1 or E1, you're most likely going to get a distribution of substitution and elimination products. How exactly that falls out, again, depends on the solvent you're using and any other additives in there. So the E1 mechanism typically comes into play with weak solvent and heat. So meaning there is no explicit base in the form cation, base, anion present. So a common reaction is the dehydration or loss of water of an alcohol to an alkene. So, based on your textbook and what you're learning in this class, you can kind of funnel your thinking into E1s, or typically with those starting materials. So in the example given, we have the dehydration of an alcohol. So the numbering that you see on the starting material is the numbering of the chain. So at the 2 position, there's an OH group. At the 3 position, you have 2 methyl groups. We're going to treat that with a strong acid, sulfuric acid, and I'm going to put square brackets around that to indicate that it's a catalyst, and our solvent is water. So what does dehydration mean? You're losing the elements of water from that molecule, and in so doing, you're forming a carbon-carbon double bond or an alkene. And what I've shown you is the 3 possible alkenes that you can form. So what you'll notice is that the product no longer has an alcohol. And then if you follow the numbering, you'll see that for some of them, a rearrangement has occurred. So that's telling us that this mechanism proceeds through a carbocation. So remember, when we ionize to form a carbocation, we have to classify it and see if it can form something more stable. If it can, a rearrangement will occur. And then what we're going to do is an elimination of a proton to form the double bond. So when you look at these possible products, so for example, in the most left one, I'm going to circle those sp2 hybridized carbons and then count the carbon substituents bonded to each so that you can classify. So based on that logic, what do you think the correct answer is? So for the middle one, this is the only one with carbon substituents. And then the last one, it's that. So if the carbon only has hydrogens, you don't count those. So the correct answer for this would be B. So that's tetra, this is di, and that's mono. And the reason we want to do that is because then we can compare it to the alkene stability trend. The more substituted an alkene, the more stable, the higher percentage of the product distribution it will be. So we would expect the tetra substituted to be the major product.
Why would the middle one like not be substituted? Because is it just because there are like 2 of the substituted?
So if you look at this carbon right here, it has a carbon and a carbon. So that's 2. When you look at this one, it's hydrogen and hydrogen. So you're only counting these carbon substituents. So of the 3 possible alkenes, which one is the most stable? So we have a butene derivative. The double bond starts at 2, so that eliminates A and B. Then we look at where the substituents are. They're on carbons 2 and 3. That eliminates D, so C would be our correct answer. So 2,3-dimethyl 2-butene. So when 3,3-dimethyl-2-butanol is treated with acid, the blank will be protonated to generate a blank that will blank, resulting in the departure of blank. So this is the verbal description of the mechanism here. So if the alcohol is treated with acid, that means the alcohol is acting as a base. So the alcohol will be protonated. So that eliminates B and D. When you protonate an oxygen, that generates an oxonium. That eliminates C. That will ionize, resulting in the departure of water. So A is the correct answer. So I'll draw the full mechanism on this slide. The subsequent questions we'll sort of answer as we go. So our alcohol is the base, sulfuric acid is the acid. I'm going to represent that as HA. So the first thing we do is protonate the oxygen. So when we do that, protonated oxygen is called an oxonium ion. So oxygen plus, and then we still have that conjugate base A minus that balances the charges. So now the water can leave. So that ionizes this bond. The CO bond breaks. So that generates a carbocation. So if we classify that carbocation, we find that it's secondary. It has 2 carbon substituents. So the carbocation stability trend was tertiary greater than secondary, much, much greater than primary. So we formed a secondary carbocation. Now we have to look to those beta carbons, so beta and beta prime, to see if we can do either a 1,2 hydride shift or a 1,2 methyl shift. If we shift over from the beta carbon, so a 1,2 hydride shift, that's going to result in a primary carbocation. That's less stable. But if we look at the beta prime, we can move a methyl group over. So that whole methyl group moves with those electrons. And that will result in the formation of a tertiary carbocation. So now we need to do the elimination. Because we move the carbocation over, we have to reclassify things. So if that's now alpha, we have these 2 betas, which are the same. And then we have a beta prime. So the elimination to the most stable product is going to come from beta prime. That hydrogen right there. So we can have the conjugate base do the elimination, and that's going to form the tetrasubstituted product. If you were to eliminate from the beta that has the 6 hydrogens, that gives you the geminal disubstituted product. So initially, we protonate, generate the oxonium, that ionizes, that gives a secondary carbocation. We have to evaluate if a rearrangement will occur. So again, here was alpha originally. That was beta, beta prime. Will this undergo a rearrangement? The answer is yes, because we can go from secondary to tertiary carbocation. It's more stable. When it does rearrange, the methyl group from that beta carbon is going to shift. So when that whole thing moves over, that carbocation then has to migrate. And so C will be our tertiary carbocation. D as in dog is what we're starting with. B makes absolutely no sense because you already have 4 bonds to the carbon, and then you're saying there's a plus charge on it. That violates the Lewis dot rules. A is when a hydrogen from this beta prime would move over. And so that's not favorable because that's primary. So we do not want to go from secondary to primary. So that rearrangement is called a 1,2 methyl shift. So if I put a red ball around that group, that methyl group migrates over from the 1 to the 2 position, relatively numbering. So the total number of beta carbons now, remember we had to reclassify that as alpha. So we have beta, beta, and beta prime. The total number of beta carbons is now 3. And then from there, you have to evaluate which one is going to do the elimination in preference of forming the more stable alkene. The total number of beta hydrogens was 7. So 3, 3, and 1. So moving to the right, if we eliminate that tertiary hydrogen, that gets us the tetrasubstituted product. Moving to the left, if we eliminate that primary, that gets us the geminal disubstituted. And so once we've figured out what are all the possible products, then we classify them. We can rank them according to stability and then predict which one's the major, which one's the minor. Any questions? So this question here, it's called putting it all together. I'll let you work through this one. This is basically using all the reactions that you've learned from modules 4 and 5 now to start with cyclohexane and then make that target molecule. So one way to think about doing this, obviously you have the possible sequences. You could run through the reaction steps in the forward direction for each sequence to see where it leads you, if that leads you to the right product. Or you look at the target molecule, identify the functional groups, and then think about the reactions in which you make those functional groups. So here we have a nitrile. Here we have an alkene. So how do you get a nitrile into a molecule? How do you get an alkene into a molecule? I'll give you some hints here. So those are the mechanisms that you would use. But then also you're starting with a saturated in the sense that all the carbons are sp3 hybridized. Molecule cyclohexane, they're all CC and CH bonds. So how do you functionalize a CH bond? What mechanism did you learn for that? And then eventually, once you figure out what steps you need, what order do they need to be done in? So give that a think. If you have any questions, shoot me an email. But otherwise, we're going to march on. So as I said, we have a lot of material to cover. We've learned how to take our substrate bearing a leaving group, eliminate it using either the E2 or the E1. Now we have the alkene in the molecule. Remember, an alkene has a pi bond that contains 2 electrons. We saw the strength of the total double bond, that the pi bond was weaker than the sigma bond of those 2. So in this next run of reactions here, we're looking at a pi bond acting as a nucleophile. So outside of an acid-base reaction, remember that where that's a proton transfer. Every other reaction, you're going to classify a nucleophile, which is supplying electrons, reacting with an electrophile, which is accepting them. So now that we've formed the alkene, what can we do with it? We can add it to a variety of electrophiles. And so for the electrophiles, they're going to be of this form. I'm going to say A, B. So A and B can be the same element, or they can be different elements. So for example, so hydrogen gas, H and H, that would be an electrophile. So A and B are both H. So in the center reaction, there's your alkene, and I've designated them carbons 1 and 2. What is one of the complicating factors here? If A and B are different in the electrophile, we have to figure out what carbon atom, 1 or 2, is getting what element, A or B. So the word for that is called regiochemistry. So looking from the alkene to the right, in terms of the orientation of A and B, if carbon 1 gets element A, carbon 2 gets element B, this is the product you end up with. Your sp2 hybridized carbons have been rehybridized to sp3. Now they're all sigma bonds. What about moving to the left? We're going to flip the orientation, B, A. Carbon 1 gets B, carbon 2 gets A. So what we have to do now is look at the substitution pattern of the alkene in the nature of the electrophile we're using. For an electrophile like hydrogen, because both elements are the same, it's a little bit easier to predict the product because all you're doing is adding hydrogen to both. But if you're using an electrophile where they're different, now this issue comes into play. What carbon atom, 1 or 2, is getting which element, A or B? And so as I said, the name for that is regiochemistry. You have two possible products that you can predict. The relationship of those, they're going to be constitutional isomers. And then furthermore, because we learned about stereochemistry, you can get enantiomers or diastereomers. So depending on which way the electrophile adds, that's called regiochemistry. And then another complicating factor dealing with stereochemistry is the face of the alkene. So as you're looking at the alkene on the board there, you have this face, like if you were going to throw a ball at that alkene, it would hit the face presented to you. If you were standing back there and you threw the ball, it's going to hit the opposite face. So the alkene has two faces, and the approach of the electrophile to either face will matter. And as you can see, it's getting increasingly more complicated to predict what the major product is going to be. So, I use this word quite a bit. You have to diagnose a lot of things now in the reaction you're presented with. So to take it to the next level of Dante's hell here, there is another term which, again, I have to think for a minute or two about this when I'm diagnosing reaction conditions, and this is called stereospecificity. And what that relates to is the nature of the starting material. So if your alkene is cis or trans, and then how that relates to what the product is going to end up with. So from that, it allows you to really predict the mechanism, how these things are adding. So in short, if a reaction is stereospecific, you can tell by looking at the product what the geometry of the starting alkene was. Was it cis or trans? And then as we look at the different electrophiles, based on the nature in which they add the elements of A and B, the timing will matter. So do A and B add at the same time? That's called synchronous. Or do A and B add at different points in the reaction coordinate? That's called asynchronous. So, for example, with H2, you're plunking down H2 synchronously at the same time. Each carbon is getting that hydrogen at the same time from the same face of the molecule. So when they add to the same face, that's called a syn addition. If they add to opposite faces, so say the element A adds to one face, and then through the mechanism, B adds to the other face, that's called anti-addition. So we have a lot of things to think about in these mechanisms. The regiochemistry, the stereochemistry, the timing. And again, this is the coalescence of all of the stuff we've learned so far on the semester. How do we ultimately determine what has happened? That's when the IR, the mass spec, the NMR analyses come into play. So here's the buffet. This is what we got to get through in the next 15 plus 9, 24 plus 75, about 99 minutes remaining in the lectures here in the semester. The overall concept is you're taking an alkene and you're doing a functional group transformation. And these are all the functional groups that you've learned so far. And related to that, what were the unique spectroscopic signatures of those functional groups? So the reactions all have names that indicate what's happening. So we'll go through each of these one by one. This is the summary of the name, what type of product is produced, the timing of how the electrophile adds to the pi bond, some details about the mechanism. Are you forming a carbocation or not? So again, then you have to consider rearrangements. What's the regiochemistry of the reaction? And is it stereo specific? So we'll go through each reaction. We'll look at an example of it. We'll talk about the mechanistic details. If I can make it through here. So a lot of these reactions, the name of the reaction is giving you an indication of what is happening. When you get into organic chemistry 2, it's not really like that, because the name of the reaction is typically assigned to the person that discovered it. So when I say hydrogenation, that should give you the idea or visual representation in your mind. The alkene is being hydrogenated to an alkane. So sp3 hybridized carbons are going, or sp2 hybridized carbons are going to sp3. Because you're starting with an electrophile with both of the elements, there's no regiochemical issue. Whether H2 adds sort of this way or that way, you end up with the same product. So both carbons 1 and 2 end up with hydrogens. The carbons are now sp3 hybridized. So the alkene shown, which is so it's a 2-pentene derivative. At the 3 position, we have a methyl group. And then we also have some geometry to deal with, and so this would be cis 3-methyl-2-pentene. So for this one, we don't really need to talk too much about the mechanism other than to say the electrophile H2 is adding across carbons 2 and 3. That's going to result in the production of an alkane. The timing of the reaction is synchronous, so each H adds to each carbon at the same time from the same face, so that's called a syn addition. This is the reaction that's used experimentally to determine degrees of unsaturation, which we've talked about quite a bit this semester. So hydrogen's a gas. By measuring the pressure differential of how much hydrogen is taken up in the reaction, you can then convert that pressure into moles using the ideal gas law. And as a consequence of that, figure out the degrees of unsaturation in a molecule. So experimentally, that's how you do it. You can also use a stable isotope of hydrogen called deuterium. So instead of adding H, you add D. Because the deuterium atom is heavier, overall your mass would be 2 mass units more than the parent. Any questions? That stool is killing my keister. So, as I said, it's going to come fast and furious up here. I know I'm not Vin Diesel or Paul Walker or anything, but we're going to jam through these pretty quick. And we'll talk about the important mechanistic details for each one. But again, overall, the name of the reaction is telling you what's happening. So the next one is hydration. So hydration is the addition of H2O. So H2O itself is not the discrete electrophile. So you have other things in the reaction mixture. So this is a stepwise process. Typically, you're running this with dilute acid, so I'm going to say hydronium, in water. So you have the electrophile as the hydronium, and then the nucleophile as water. There's our model alkene. That was the cis 3-methyl-2-pentene. So when we identify the double bond, we're going to add the elements of H2O across that. It doesn't happen all in one step, but overall you've added an H and an OH. And now we have that issue of regiochemistry. So when I look at the product that says the major product, I look where the alcohol is, and I classify that alcohol. That's a tertiary alcohol. I look at the minor product. That's a secondary alcohol. So I know they are different things. For the hydrogenation experiment, remember, since you added H to both, there's no regiochemical issue. So what guidance can we use for this? So Markovnikov's rule states that when you examine the alkene, the carbon that will bond to the alkene is the one that or the carbon of the alkene that will bond to the electrophile is the one that starts with the most hydrogens. The reason for that is because it's going to generate a carbocation. So ultimately, that will produce the most stable carbocation, which the nucleophile will attack. So stated another way, Markovnikov's rule is them as has gets, or the rich get richer. In this case, our electrophile is H plus or proton, and the nucleophile is water. So how does this happen? So that was the major product. The pi bond of the alkene is going to act as a nucleophile. It's going to supply 2 electrons that will react with that acid. So I'm going to just number this 1, 2, 3, 4, and 5. That's the numbering of the chain. So if the pi bond is abstracting a hydrogen, that can be either bonded to carbon 2 or carbon 3. So you have a choice. You have to evaluate each choice, because at that point it's going to form a carbocation. So I want to bond that H to carbon 2. So I'm going to say C2. Now when I do that, carbon 3 ends up as a carbocation. If we classify that carbon, it's tertiary. So a tertiary carbocation. In the alternative pathway, if we bond that H to C3, and classify that, that's now secondary. So we always want to form the more stable carbocation. So that's formed preferentially. Now the carbocation's electrophilic. We're in the presence of water. Water supplying electrons. It's going to trap the carbocation. That was called an oxonium ion. We get another molecule of water to do an acid-base reaction. And that's going to lead to our major product. So we've added the elements of H2O to that pi bond. The mechanism tells us that H adds at one step, the OH adds at another. So the timing of this is asynchronous. So the H and the O are adding at different steps along that reaction coordinate. The timing's different, so that's asynchronous. Questions? So we'll ask some questions about that, but for a lot of these reaction mechanisms, remember the pi bond has 2 electrons. It's acting as the nucleophile to begin with to add something. Then if it's proceeding through a carbocation intermediate, that's electrophilic. And then the second element is coming in to attack that. So what form of spectroscopy would be best used to identify the presence of the alcohol in the molecule? So we want to prove there's an OH group. It's going to be A. So the reason it's IR is because, remember, every molecule has CC and CH bonds. What's unique about that functional group, it's OH. And then in region 1 of the IR, that OH stretch, it's going to be nice and broad like that, come back up, and then come back down into your CH stretching. So those are some diagnostic things you want to commit to memory. Your final is probably going to have 2 to 4 spec problems on it. And, since there's only 2 to 4 of them, you just want to make sure that you're covering the broad range of these functional groups. What are their diagnostic signatures? So the first step of that mechanism for hydration really was an acid-base reaction because you were doing a protonation. But in general, everything after that, the carbocation was electrophilic, water was nucleophilic. And so it's important that you understand how the electrons are flowing. So your alkene, and then most of these mechanisms hold true for alkynes because the alkyne, it's just 2 double bonds now. Alkene or alkyne is the nucleophile. You can generate a carbocation, and then remember the stability trend. So when you're thinking about the regiochemistry of what carbon gets the electrophile initially, do yourself a favor and draw both pathways, then evaluate. This is a representation of what we just went through, so I'll laser over it. There's the pi bond. In the green route, that's the preferred pathway. The red route is the not preferred. The pi bond is abstracting a hydrogen from hydronium. So if you look at those two carbons, that's the carbon that has the most hydrogens. So that's the Markovnikov's rule. When that gets protonated, it generates the tertiary carbocation, which is more stable. Remember that a carbocation, the plus charge, resides in a p orbital that has two lobes. The nucleophile can attack from the top or the bottom lobe. So that's the stereochemical issue, if there is one. If you went and protonated the other carbon, you generate the less stable carbocation. Then you have this issue of how that nucleophile attacks from the top or the bottom. Notice now in this case where I've put these blue asterisks, that represents your forming stereogenic carbons. The bottom case with the tertiary alcohol, that's neither of those carbons are stereogenic. So ultimately you don't have to worry about stereochemistry. So we'll get through one more today. Essentially the same mechanism as hydration, but the name of this is called hydro, so you're adding H, and then halogenation. So hydrohalogenation, you're adding the elements of HX, where X is a halogen. And we know that for HX, those are acids, right? So hydrochloric acid, hydrobromic acid. So let me back that up. So for example, if we use HBr, now the elements of the electrophile are different. They're two different things. So what's getting the H and what's getting the Br? It turns out the mechanism proceeds similarly to that of the hydration because of the Markovnikov rule. The major product ends up being the tertiary bromide. The minor product is the secondary. So we protonate the carbon that has the most hydrogens. That generates a tertiary carbocation plus the bromide anion. That will then trap the carbocation. Now, even though I didn't show it, it can trap from the top or the bottom. In this case, it doesn't matter because where it traps, you're not generating a stereocenter. But for the most part, you want to draw both products of it trapping from the top and the bottom and then compare them to see what their relationship is. So we're about out of time, so we'll end it for today, but we're going to continue on with Wednesday with the other addition reactions. What are the other electrophiles we can use to make these other functional groups?